By the end of this lesson, you will learn to create and code these beautiful geometrical shapes with your students. Along the way, they'll discover how to find the exterior angle of a regular polygon. And for those of you who have never coded before, this will be your first time coding. The link to the lesson plan can be found in the descriptions of this YouTube video. In the lesson plan, let's click this to enter the dojo. Enter in your name and you're ready to go. For this lesson, you'll only need 3 commands: forward, right, and left. To do so, let's click the first command, forward. You'll notice that the arrowhead moves forward by 50 units. What we can do is we can change this 50 to something else, like 100, to change how far we moved forward by. So that's the first command. The second would be face right. Click it, you'll notice that the arrowhead faced right by 30 degrees. Once again, we can change this 30 to say 90 degrees. So far, you've been clicking, but you could also type this out. So if I want to move forward, I will say FW space 50. So that's 2 commands. The third command you'll learn is face left. So if I click face left, you will notice that it turned left by 30 degrees. So that's all the 3 commands you need for activity 1. For activity 1, students are to use these 3 commands to form a square, triangle, hexagon, and pentagon. Pause the video now to try drawing these shapes for yourself. I'll do the square real quick right here to give you an idea of what it looks like. To draw a square, let's see. It's basically a forward command, followed by a right turn, followed by forward again, and a right turn. And I repeat this 4 times. And there you go, we have a square. The code for all of the shapes can be found here. So if you wish, you could simply copy and paste it here. And this will be the equilateral triangle. The next shape to draw is a hexagon. Now, chances are when you drew the hexagon, you calculated in your head what the turning angle should be. But for students who don't know the formula to find the exterior angle, what they will likely do is they'll do a trial and error approach. So for example, they might try something like this. So they'll try a different angle, and they will realize that this doesn't really draw a hexagon. Now, this is a very important teaching moment for the students, because as they embark on the process of finding hexagon, they'll realize that this doesn't really form a perfect hexagon. Now, the question to ask the kids here is, do you think that in order to draw the hexagon, you have to turn more each time or turn less each time? Well, so the student might say, I would want it to turn more. What you would do is tell them to increase this 65 degrees by a little bit. So let's make it possibly 70. So we'll change this all to 70. And you see what happens? Well, then you ask them the question again. Does turning more make it closer to the hexagon you have in mind? Then they might say no. Then you might prompt them and say, what if we try a number that's less? And there you go. So the process of nudging the value up a little bit or down a little bit to figure out what that does to the shape is a very important part of exploring geometrical shapes. It's also a very important part of exploration. We're probing a little bit here and there to see what happens. Next, you have to draw a pentagon. Chances are students don't know what a pentagon is. At this point, it's again an important teaching moment. I suggest you ask the class, does anyone know what is a pentagon? And if there's a kid that knows what's a pentagon, get her to stand up and explain it to the rest of the class. There's also a chance that no one knows what's a pentagon. In that case, I like to wait for the kid that is the fastest and reach the pentagon question to ask me what's a pentagon. Then I'll get him to Google it up for himself, what's a pentagon. As an added bonus, if he is able to draw the pentagon himself, the thing is the students will be able to see from the sharing panel who has done the pentagon. When the other students see that he has done the pentagon, I'll get him to go and teach the other students how to draw the pentagon. That brings us to the end of activity 1. At this point of the class, I like to take the chance to teach the students more about the etymology of the word polygon. What does the word poly mean, and what does gon mean? This is also a good time to consolidate their learnings. I would draw this table on the whiteboard, listing down all the polygons they've drawn so far and their turning angle, which is the exterior angle. The question to ask at this point is whether they're able to spot any patterns. A few possible observations are listed here. From their observations, we will get them to make a hypothesis on the relationship between the number of sides of the polygon and its exterior angle. So in the next activity, the students are to test whether their hypothesis for this relationship holds true by finding the turning angle for the octagon, hexagon, and hexatriacontagon. And yes, I did practice that. Before starting on activity 2, we'll introduce a little trick to help reduce the number of lines of code they have to write for drawing the polygons. At this point, they should notice that the polygons are basically just 2 basic commands repeated over and over again. Instead of copying and pasting this multiple times, what you could do is you could open up the command deck, highlight these 2 commands, and indicate that you want to repeat this 5 times and click this. This basically creates a loop. It does lines 3 and line 4 5 times. So if we were to use this loop command, we could change the number of times we loop to 6, and we could change the turning angle to 60, and we can get a hexagon. So the loop command will be coming in very handy when the students approach activity 2. So in activity 2, students are to draw an octagon, a decagon, and a hexatriacontagon. When the students are done with activity 2, it's time to formalize their learnings here. By filling up the table, they should have further validated their observations from before, which is that the number of sides of the polygon multiplied by the exterior angle should give you 360. Or put it a different way, the sum of the exterior angles or the turning angles should be 360 degrees. Now the question for the students is, why is the sum of exterior angles 360 degrees for a regular polygon? It's interesting to hear what the students come up with. Generally, there are 2 ways in which I would explain this. The first way is through a physical representation. So to do so, I would get a student to stand up and try to draw an equilateral triangle. So I'll give them commands and they will have to follow. So I'll say, move forward 3 steps, then turn right 120 degrees. Move forward 3 steps again, turn right by 120 degrees. Move forward 3 steps, turn right by 120 degrees. At this point, they would have drawn out a equilateral triangle with their bodies by walking. Now, for the second part, I'm going to change the instructions a little bit. I'm going to give the same set of commands, but this time, when I say move forward 3 steps, don't actually move forward 3 steps. In the second part, what the students should realize is they will only be turning on the spot 120 degrees each time, and by the time the shape is complete and the instructions were complete, they would face back exactly where they were facing before. You could do so with any of the regular polygons, and you'll see the same thing. In order for the shape to complete itself, the students have to turn 360 degrees. That's why the summation of the turning angles is 360 degrees. So that's a really good way to do so via physical representation. Another excellent way to do this is through visual representation. So if you were to extend a line outwards from the edge of the polygon, you could see that as I make the polygons smaller and smaller, it approaches this shape where the sum of the turning angles is 360. So that's another interesting visual representation of why it adds up to 360 degrees. And this exterior angle times number of sides equals to 360 degrees is the formalized mathematical formula which we want them to walk away with. If you rearrange it, you can get the exterior angle equals to 360 divided by the number of sides. And ta-da! The students would have discovered for themselves through observations and pattern recognition and their own hypothesis of how shapes are formed to come to the conclusion that this relationship can be expressed in this mathematical formula, which is a beautiful thing. Using their newfound knowledge comes the most interesting part of the class. So in activity 3, the students get a chance to be creative in the gemstone crafting session. The task is for them to use polygons to craft a gemstone, kind of like the ones we have shown here. They get bonus points if they are able to use a polygon with a number of sides that we have not gone through in class. And that's it for activity 3. And I know that having class time for something creative like this is a luxury, and some teachers might think to omit it. But I really encourage teachers to make time for this, because giving the space for students to use the mathematical ideas that they have learned to create works of art like this gemstone, it really helps to personalize their learning and make the learning relevant to them. Mathematics is often very abstract, and giving a chance for them to use it and apply it to create simple things like art, like this gemstone, that is unique to them, I think really helps with solidifying the learnings and making it special for the students. And so yeah, that's it for this lesson plan on gemstones, on polygons. And I hope that your students enjoy the lesson. If you really do try this out with your students, please write to us and give us some feedback on how the lesson went for you. Yes, so looking forward to your response. That's all from us.